Hello, this presentation will talk about how to use texture maps in a C++ OpenGL program. There's an enormous variety of different ways that texture maps can be used, and I'm only going to discuss one of the simplest methods just as an introduction to how to use texture maps. It's also the most commonly used type of method as well. So you can find this material discussed in Chapter 7 of the online PDF. There's also a couple C++ programs, Texturebmp Modern and For Textures Modern, that'll show how to read texture maps from a .bmp bitmap file and how to use one or more texture maps when rendering so as to put texture images onto surfaces. So I'm going to give a sort of overview of what's going on without getting into a lot of details, and then we'll take a brief look at the source code for Textures Modern. So the general setting is the following. We've got a C++ program that has to initiate things, and it starts by loading the texture maps from files. So texture map is read from a file. If there's multiple texture maps, they're read from multiple files. In our code, we'll use a C++ class called RGBImage, which I wrote to help us with this. It then loads the texture maps into OpenGL's memory, which presumably would actually put it out on the GPU as needed, possibly setting all theirs all the time. And then it sets parameters, and this is things like whether to wrap in the S direction or the T direction, and also whether to set to do MIP mapping. Okay, and that's the preliminary work. And then when you're rendering a surface, we'll use a function called glBindTexture to select a particular texture to be used when rendering. There's no reason you couldn't use more than one texture. You certainly could when rendering, but we'll just do examples where you only use one texture at a time. So that's basically the highlights of what the C++ program does. The GLSL program I'll describe on the next board. The shader program, or GLSL program, uses the texture map when rendering. Typically, this is the fragment shader doing the work, and we're rendering a particular pixel on the screen with the fragment shader, and it's going to look up a particular value out of the texture map here. It has a uniform variable of type sampler2d, and this is the name or pointer to the texture map itself, and it uses a function just called texture, and this function texture takes in the shader program, the sampler2d object, and the texture coordinates that produces the texture map value. And then it's a GLSL program, then it does whatever it wants. It's just a program. Typically, it would just paint it in or multiply it into the color on the surface, but it is, since it's programmatic, you can do anything you want, really. But that's a little bit maybe overly general, so let's be more specific. the common usage with Phong lighting or other local lighting models is to use Phong lighting on white or gray objects. So the Phong code uses white or gray materials and lights so that everything is just rendered bright, something between dark and bright white. And then you multiply the resulting color by the texture map value. Now this isn't quite good enough because what happens here is it messes up the specular highlights when you do this. You expect even black objects to have specular highlights on them, but if you do it as I just wrote it here, when you multiply by a black texture map value, it will wipe out the specular highlights as well. So the fix for this is to do what's known as separate specular highlights. And so for separate specular heights, the calculation Phong calculates out the eye value. Remember, that's the illumination as seen by the eye, as a sum of two parts. There's the specular part, and then there's the non-specular part, which I'll just spell out. I sub non-specular. So I sub non-specular is the combination of the emissive, diffuse, and ambient colors. So in other words, that's I sub S plus IA, the ambient part, ID, the diffuse part, and IE, if there is one. And all those three things together are the non-specular part. And then in this case, you then set the pixel color to be the following. It's the specular value, that's the specular highlight, plus the texture value multiplied by the non-specular component of the Phong lighting. In this way, the texture value serves as essentially as the color of the object. It's affected by the ambient and diffuse lighting, and so it gets brighter or darker depending on the lighting, but the specular part is largely independent of the color of the object, so we just add it back in separately without multiplying it by the texture map value. Now I want to very briefly go over the commands that are used by both the C++ program and the GLSL shader program to access texture maps. So we'll start with the C++ program. So these are the OpenGL function calls and one other thing that can be used by the C++ program to work with texture maps. So the first one is there's a class of objects, RGB image objects. This is written by me, but it's used to read bitmap files. These are .bmp files into C++'s memory. And this lets you just read a file of a texture map, raw data with colors. And this is for 24-bit bitmaps. And then there's the OpenGL function call, glgen textures. And this is used to generate names of textures for OpenGL. So the names are just unsigned integers, and they're just a way to refer to textures when you're making OpenGL calls. The function glbind texture is used to select a particular texture to be the current active texture. So this is used either when setting parameters of a texture, you would bind the texture first and then set its parameters, or when rendering, you would bind a texture and then render using that texture. There's GL tech parameter I. We already saw some examples of this in earlier presentations. So this is to set parameter values. For instance, wrapping and MIP mapping are controlled by calls to GL tech parameter I. I means we're passing in integer values. There's GL tech image 2D. So this is used to load texture data from C++'s memory into OpenGL's memory. So we load a texture map into OpenGL's memory. In particular, OpenGL might go ahead and store this out on the GPU, on the graphics processing unit. And last one I want to list is GL generate MIP maps. So for this, it generates MIP maps. After you've loaded the texture map into OpenGL's memory, you can get OpenGL to automatically create all the MIP map levels for you by calling GL generate MIP maps. It is possible to create your own levels of MIP maps, but OpenGL has this very handy routine. That's what you would usually use instead. Shader program also has a few commands for working with textures. And this is typically the fragment shader. In fact, almost exclusively the fragment shader, really. And the fragment shader, it has a couple variable types. There's the uniform variable of type sampler 2D, and let me just give it a name, text map. Okay. And this is just a variable that refers to the value of it, gives you the value of a texture, perhaps usually GL texture 0, for instance, the default texture map. And then there's a vec2 variable, which I'll call textwords. And this might be an in variable, or it might be a variable that's computed elsewhere, or something like that. And then there's a GLSL function, texture, which is used to access the value of a texture. And it takes in a sampler 2D object, namely a texture object, and texture coordinates, in our case, ST coordinates, and it returns the value of the texture as indexed by those texture coordinates. So it returns the texture value for those texture coordinates. And this is a very powerful but simple to use function. It's very powerful because it does everything you want it to do in terms of bilinearly interpolating between pixel values and linearly interpolating between MIP levels. All of that's done for you when you call the texture function. Okay, so for the remainder of this talk, I'm going to move to the computer and I'm going to show you the for textures modern code very briefly to let you see the actual C++ and GLSL commands that are used. For the second part of the talk, we'll be looking at the for textures modern program, especially the C++ code and the GLSL code. Here's the web page for the program. The image here shown in the middle is what the program does. It just draws 4 rectangles with 4 textures attached. There is some explanation online of the HTML features, which you can see right here. I'm not going to go over that, but you're certainly welcome to read it separately yourself. So here's the C++ program, for textures modern.c++.cpp. And let's start off with the texture reading. There's an array at the front with the names of texture files. There's an unsigned integer array of texture names that will be generated by OpenGL. These are read in by the function myLoadAllTextures, and we first generates the texture names, and then it loops over the texture names. It calls there's an RGB image type called TextMap. We do a load BMP file function with the file name passed in to read the ith texture into the text map. We do GL bind texture to get the ith texture name bound. GL texture 2D means we're working with two-dimensional textures right now. We set some parameters, namely it repeats or wraps in the S direction, it repeats, namely wraps in the T direction, and we do the GL linear for the GL texture mag filter, which is the bilinear interpolation between colors on pixels in the texture map, and the GL linear mip-map linear, which is the bilinear interpolation plus linear interpolation between mip-maps for cases where the texture map has higher resolution than the screen. We get the texture width and the texture height from the text map using getNum calls and getNum rows. We call the C++ function, or the OpenGL program, GL text image 2D, which does the following. It's a two-dimensional style texture. It's the 0th level of the mip mapping. It holds RGB values. It's got this dimensions, and it's storing those RGB values as unsigned bytes. So that means the colors are ranging from 0 to 255. And then this is the pointer to the texture map data in the text map object. And the GL text image 2D reads the data out of the text map RGB image object and stores it into OpenGL's buffers. And then we generate the mip maps by calling GL generate mip map. We get the name of the variable called the texture map in the shader program. We'll look at that in a moment. And we set it to use texture map number 0. And just in case, we set GL texture 0 to be active. In myRenderScene, when we're rendering something, we select the shader program to use. This program has only one. We call GL bind vertex array to pick its object to render, GL vertex attrib3f to do the color, which is white, and then we call GL bind texture, GL texture 2D texture name sub 0. That gets the texture number 0 as loaded earlier and uses it when we draw the first triangle strip. This triangle strip draws a rectangle. Then for the next rectangle, we use the GL bind texture with texture name sub 1, the next one with texture name sub 2, and the texture names sub 3. And that renders the 4 rectangles as triangle strips containing 2 triangles each, and each time we use a different texture map. And that's everything that's in the C++ program. So now we'll go look at the GLSL program. So now we're looking at the file Texturebmp modern.glsl. This is the vertex and fragment shader for 4 textures modern. And this is really, really simple. There's no Phong lighting involved at all. We're just going to be applying a texture on top of a white color. So the vertex shader comes first. So there's a begin the vertex shader command here. The name of the vertex shader is vertex shader pause color only. It has in variables are the vert position, the color, and the texture coordinates, and out variables, which are the color and the texture coordinates. It computes the position just directly off the vert position. There's no transformations, no nothing. The color just copies off the vert color. The texture coordinate is just copied over from the vert texture coordinate. Those values are out variables for the vertex shader. They're in variables for the fragment shader, which is right down below. So here's the fragment shader. It's got an in vec3 for the color and in vec2 for the texture coordinates. And these texture coordinates are averaged using a kind of barycentric interpolation, although strictly speaking it's using hyperbolic interpolation. It's essentially the same in this setting though, because we do not using perspective. More important for our purposes then is there's the uniform sampler 2D, which is named the texture map, and there's the output is the fragment color, which is the color that will be used for the current pixel. The fragment shader is run once for every pixel, and it uses the texture command, passes in the texture map, passes in the texture coordinates, and multiplies results by the color, and uses that as the frag color, which is the color of the pixel. In a more sophisticated setting, you would use Phong lighting, and you would have separate specular color, and you would multiply the texture map times the non-specular color, and then add in the specular color separately. But in this simple example, there is no Phong lighting. We're just illustrating the use of texture maps. And that's the end of this presentation. Thank you very much.